I know you guys are kind of filled up today, like after having lunch, and I know that you guys can't concentrate today also, like because you have the class assignment today. But this is going to be a really interesting topic, I guess, because this contains like programming, statistics, and mathematics. So we are group 4, and of course we are one member short today, but somehow we think like we will be able to manage it somehow. So I'm Charles Pereira,
And I'm Clara again.
so we'll be presenting recursive functions today. So these are the topics that we'll be discussing today. So I'm not gonna read this out now because we'll be elaborating on these topics in our future slides. So before moving into recursive functions, do you know what is meant by recursion? So recursion is the process through which a function calls itself repeatedly, directly or indirectly until a certain condition is met. So in computer science, this recursion comes into action when solving a problem by breaking this problem into smaller subproblems. So in computer science, we define these smaller subproblems as instances. So recursion can be only applied if we can divide this complex problem or this original problem into smaller subproblems. So I have a small
Recursive function is like a Russian doll. Each time you open a doll, a smaller one will be inside, and you repeat the process until you reach the smallest doll, which doesn't contain another one.
So this Russian doll example is the ideal example to explain this recursive function. So as you saw earlier, this bigger Russian doll, when you open this bigger Russian doll, you can find some smaller Russian dolls in it. So how can this relate to computer science? So if you take a problem, so you can assume this our bigger problem or our complex problem or our original problem as this bigger Russian doll. So when you open up this bigger Russian doll, you can find some smaller Russian dolls in it. So it's like that we can expand this complex problem into smaller subproblem of itself. So I have a small question for you guys. So do you think that we can divide each and every problem into smaller subproblems? What do you think? No. So that's correct not, because we can use recursion only if we can divide a problem into smaller subproblems. So the next question is, how can we divide a given problem? So there are mainly two components of recursive functions, which are base case and recursive case. So base case is the simplest version of the problem. So it's usually referred to as the stopping condition or the terminating condition. When it comes to recursive case, so I told you earlier that we can divide this complex problem into smaller problems now. So we call these recursive functions on these smaller subproblems in order to get the final output. Right? So this recursive case will be executed until it reaches the base case, because base case is the simplest instance of this problem. So this is a kind of a mathematical interpretation that we can explain how recursive functions execute. So here we have the problem of prime sum of n natural numbers is a recursion. So our original problem or the complex problem is sigma n, right? Sigma n is our complex problem. So how can we divide this complex problem sigma n into smaller subproblems? So we can divide this as n plus sigma n minus 1. So don't worry if you didn't understand this, because we will be elaborating more on this in our future slides. Next comes steps of designing a recursive algorithm. So recursive algorithms are a powerful tool in computer science as well as in problem solving, where we can solve a problem by smaller subproblems and by calling recursive functions on them until a certain condition is met. So the first step is defining the base case. So I explained to you earlier what the base case is. So base case, in simple terms, it is the terminating condition or the stopping condition of our problem. So it is very much crucial to identify whether we have one or more base cases in our problem. Then the next step is divide the problem into smaller subproblems. So here we have to determine how we can express or how we can decompose our complex problem or our original problem into smaller instances of itself. And we should be very mindful that these smaller subproblems should be the same type of this complex problem. So here we basically understand the recursive structure of our problem. Next comes defining the recursive case. So in our earlier step, we divided this our whole problem into small subproblems now. So now here we have to call our recursive functions on each of these smaller subproblems in order to get a final result. So this recursive case will be executed until it reaches the base case. Because base case is the stopping condition of our problem. Next comes combining the solutions. So once the base case is reached, we have to combine all the solutions that we got through recursive calls to get a final result. So this step may include like some additional mathematical computations and manipulation of some results that we obtain through our recursive calls. So here we have to combine those results to produce a final output. Then the last step is testing and validating. So this step is very crucial because here only we identify what are the errors in our problem. So here once we pull up all the above steps, then we have to move on to testing stage where we have to test our problem by inputting different inputs including boundary cases and very large inputs to confirm whether we get the correct result. And if we encounter any bugs during this execution, so we have to debug it and test it. So now my friend Tihara will be explaining more about how you can use these steps using an example. So over to you.
Thank you, Darshit. Okay guys, so now we will use a small example to understand how these recursive functions work. Let's say people are standing in a queue to get bread. There are 5 people, there is A, B, C, D and E. So each person will have the number of breads according to their position in the queue. So A will have 1 bread, B will have 2 breads, so on. And the problem given to us is to count the total number of breads each person has in front of them. So he has to add his breads plus the number of breads with the people in front. So A will have 1 bread, B will have 1 plus 2, that is 3 breads, C will have 6 breads, and D's answer will be 10, and E will have 15 breads. Now E is a bit of a lazy fellow. He is smart as well as lazy. Now he thinks, why should we do all of this to get just one answer? He thinks, isn't there some easier way to get the same answer? Now when he keeps on thinking like this, he gets his idea. If he can get D's answer, he will just have to add his best to that. So he asks D for his answer. Now D also thinks that this is a good method and D asks C for his answer. Now this process will continue over and over until D finally asks A for his answer. Now for A, the answer is pretty straightforward. For A, the answer is 1. That is because there is no one in front of him. Now A will get his answer and give that answer to B. Now B's answer will be 2 plus A's answer, which is 1, and the final answer B will get is 3. Now B will give this answer to C. Then C's answer will be 3 plus B's answer, and his final answer will be 6. Now this will happen until finally E gets his answer. Now E's answer is his number of breaths, which is 5, plus D's answer, which is 10. So the final answer will be 15. Now for any recursive function, there should be 3 conditions. The first condition is we have to divide the bigger problem into smaller problems. Now here we got E's answer very easily because he just had to take the ready-made answer from D and add his breaths to that. The second condition is the base condition. Now for A, the answer was 1. That was the simplest way to go. So that is our base condition. For every recursive function, there has to have this base condition. And the third step is, once you have this answer for the base condition, you just have to work your way back upwards the chain. Here, when we got 1 as the base condition, we have to go back until we get E's answer. This is recursion in simple. Now here we have solved the problem of finding the total, the sum of numbers from 1 to n. Here n is 5. Now we'll move on to recursive backtracking. Now what really is recursive backtracking? Recursive backtracking is like an algorithmic technique which can be used to solve problems which can be expressed in a search space or maze-like structure. It is particularly useful for solving problems such as maze generation, problem solving, pathfinding, and Sudoku. The basic idea behind this recursive backtracking is to systematically explore all the possible solutions until a solution is found, or until we explore all the possible outcomes. When going through a problem, our recursive algorithm works by exploring each step of this recursive function, and if it meets an invalid solution, it will go back to a previous step and check another solution. This process is done over and over until a valid solution is found or until all the possibilities have been explored. So how does this recursive backtracking relate to recursive functions? The concept of recursive backtracking is derived from the concept of recursive functions, where we use recursive functions to explore the options and to go back. We call it backtrack when necessary. And also, the algorithm for recursive backtracking is written using recursive functions. In recursive backtracking, the search process is divided into many stages, which represents a path we can use to solve our problem. At each of these steps, a recursive function is called to explore the consequences of this particular step. Okay. So there are several steps which our algorithm takes to solve this backtracking problem. First, our algorithm will start at a given initial state or position. Then it will make some choices as to the next step to be taken from the available options. And it will explore the consequences of this choice. If it finds a valid solution, the algorithm will give that as the answer for the problem. If it meets an invalid solution, it will backtrack to a previous position and will choose another option. Now these steps from 2 to 5 is followed until all the possible options are explored or until we get a valid solution. And when we get this valid solution or when these possibilities are explored, the algorithm will be terminated. Now let's take a small example to understand the logic behind this recursive backtracking. So we can use the problem of finding the path when you go through a junction, a maze, finding the path when you go through a maze. So every time you come into a junction with multiple ways or multiple junctions to follow, you just have to follow one junction and see if it comes to a solution. If it doesn't come to a solution, you have to go back to the previous position and check another junction. Every time you have to make a series of decisions, you might end up making a wrong decision. And that's okay. When you realize that you have made this wrong decision, you just have to go back or backtrack to the place where you made this wrong decision and start again. How the recursive backtracking works in a algorithm is a bit difficult to see. First, we have to define the maze. So to do that, we will allocate numbers for each point within this maze. So point 0 0 will be connected to point 1 and point 3 respectively. And for any backtracking algorithm, there are 3 keys. We have several choices to use to solve this problem, and there can be certain constraints when exploring these choices, and at the end we want to reach a goal. That is, you have a decision space to choose from. These choices can be restricted somehow, and at the end your goal should be to do something or to solve a problem. Now let's see how our algorithm solves this problem of going through the maze. So as I told you, this algorithm will first define the maze by allocating points. And it will also make a list of the points which we take up to the current position from the starting position. For example, if we are at point 4, the algorithm will take down a list of 0, 3, 4. And it will also take down a list of the numbers which we follow, and if we encounter a dead end, it will backtrack them, so then it will take down those points as well. So for example, if we are at point 2, we can't go further than that. So even so, the algorithm will take down the points 0, 1, 2. So our algorithm will solve this maze like this. First the algorithm will go through 0, 1, 2. Now there is a dead end here. So it will backtrack to point 0 again, and it will try the option of 0, 3, 6. Now that is also not a valid option. So it will backtrack to point 3, go through 3, 4, 5. Here also there is a dead end. So it will backtrack to 4, go through 4, 7, 8. Now already to go to 4, we have gone through 0, 3, 4. So our final solution is 0, 3, 4, 7 and 8. So as we know now, the solutions which the problems which we use for this recursive backtracking have several solutions, and we have to explore all these solutions. Let's take the example, if there are 2 boys and 1 girl in a class, and there are 3 chairs which you can sit on. So there are 6 possible ways to make this seating arrangement. And the normal problems which is solved using this recursive backtracking have some constraints attached to it, and we have to solve this problem by satisfying those constraints. Here we will impose a constraint saying that the girl can't sit in the middle, and at the end you want to reach the goal of finding the possibilities for this problem. To solve this, we can use a space tree. We call this a state space tree. So first our algorithm will go through points. The boy will sit first, and we will let the boy 2 sit next, and then the girl will sit. So this is a valid solution. So next, boy 1 will sit and the girl will sit. Now this is not a valid solution because we have received a constraint saying that the girl can't sit in the middle. So we will have to stop this branch from here. Next, boy 2 will sit, boy 1 will sit and the girl will sit. This is also okay. And then boy 2 will have to sit and the girl will sit. Now this is also not a valid solution because the girl can't sit in the middle. Now this process will be done over and over until all 6 possibilities are found, and we will have to get the correct solutions from them, which is those 4 solutions, the first one, third one and the 5th one. So now Tavish will explain how the recursive functions apply in the programming language.
Thank you, Vihara. So now I'm going to talk how we can code how actually we can code recursive functions. So since all of us are familiar with Python, I'm going to code recursive functions using Python. So first, let's start with a simple example. So I know all of you know what factorial is. So factorial of a given number is the product of all positive integers before the number n. So for example, so this side of the board is more visible to you guys. Oh, that's it. This one, right? right? So factorial of 0 is equals to 1. Then what is the factorial of 1? 1. Then factorial of 2? We can calculate factorial of 2 by multiplying 2 into 1. We get the answer as 2. Then factorial of 3 will be 3 into 2 into 1. So likewise we can calculate the factorial in this way. So can we write this 3 into 2 into 1 in another way? Can you guys think of something? How can we express this in another way? Like, can we break it down into a smaller problem? So we can also write this as 3 into, so I can write this part as factorial of 2. Do you agree? Because 2 into 1 is the factorial of 2. So I can write factorial of 3 as 3 into factorial of 2. So what I have done here is I have divided this complex problem or this original problem of factorial 3 into a smaller problem. The smaller problem is 3 into factorial of 2. Then the computer has to calculate, okay, then what is factorial of 2? So that is what I have done. I have divided this complex problem into smaller subproblems. So if you are asked to calculate factorial of 0, can I like divide it any further? No, right? And even factorial 1, can I divide it any further? No. No. So these conditions, which we can't divide any further, we can interpret these, like we can define these conditions as base cases. So I told you earlier, base case is the simplest version of the problem. So in this problem of factorial, this factorial of 0 and factorial of 1 is the simplest version of the problem, because we can't divide it any further. But when it comes to any other number larger than 1, we can divide it actually to some small problem. So this case we call as recursive case. So if you are asked to find the factorial of n, so how can you find the factorial of n? According to this method, so how can you calculate? So here when you are asked to find the factorial of 3, you say it is 3 into factorial of 2, which is 3 minus 1. Then we can write factorial of n as n into factorial of n minus 1. Do you agree?
Yes.
Then we identified the base case and the recursive case. So let's code this using Python now. So we recently learned how we can actually create functions in Python. So I don't know if you can
Please shut
remember.
down your machines. Shut down your machines. Here we go.
So we can define a function in Python using the keyword def. So now I'm defining the function which is factorial, and I'm giving the parameters n. Then the very first step is to define the base case. So what's the base case here? Is factorial 0 is 1 or factorial of 1 is 1. So I can say if n is less than or equals to 1, the result is 1. Right? So I can say if n is less than or equals to 1, result equals to 1. Then we have to define the recursive case. So the recursive case will be if you are asked to find the factorial of n. So we can interpret this factorial of n as n into factorial of n minus 1. Now I'm going to define the recursive case. Result equals n into factorial of n minus 1. Right? So what I have done here is I have called this factorial, I have called this function again in this in the subproblem of this complex problem. So this is what we call as recursive functions, right? It means calling the same function itself again and again in the smaller subproblems of this complex function. So that is what we call as recursive functions. So now we have to combine the solutions that we got through recursive calls. So I'm asking to return result. So then we come to the very last step, which is testing and validating. So now I have to test whether my code is correct or not. So I'm asking to print factorial of 5. So do you know what is factorial of 5 is? What's the answer for this? What is factorial of 5? 120. So when we run this code, we should get the output as 120. So let's see whether we get the output. So we get the output as 120. So, but we can't stop testing by now because we have to check even boundary cases. So boundary cases are we have to check whether it gives the correct output for base case even. So we have to check then whether we get the correct output if I ask to print factorial of 0. So what should be the answer? So it prints 1 when we ask to print factorial of 1, 0. Then let's ask to print factorial of 1. So it's print 1. So then I can confirm that my code is free from bugs. Right? So then we'll move on to another example. Which is Fibonacci numbers. So have you heard of this word Fibonacci? So I hope you haven't heard. So Fibonacci numbers are a series of numbers where each number is the summation of the two preceding numbers. For example, so what you have to remember is these Fibonacci numbers always starts with 0 and 1. So if you are asked to print Fibonacci 0, it will be 0. And if you are asked to print Fibonacci 1, it will be 1. And then if you are asked to print Fibonacci 2, so you have to remember this Fibonacci series always starts with 0 and 1. And then this each number is the summation of the two preceding values. So what are the two preceding values before 2? 0 and 1. So it should be the summation of 0 and 1. So Fibonacci 2 should be equal to 0 plus 1, 1. So I'll take another example. should be the summation of the two preceding numbers before 3. So what Fibonacci, so the two preceding numbers before 3 are 2 and 1. So Fibonacci 2 is 1 and Fibonacci 1 is also 1. So the summation of 1 plus 1 is 2. So Fibonacci 3 will be 2. Okay. So actually I can divide this complex problem, this original problem, into smaller subproblems. In other words, I can write, if someone asks to print Fibonacci of n, I can write this as Fibonacci of n minus 1 plus Fibonacci of n minus 2, because Fibonacci number is the summation of the two preceding numbers. So the two preceding numbers before n is n minus 1 and n minus 2. So can we divide this Fibonacci 0 into any other subproblem? Can I divide? No, because there are no two preceding values before 0. And can we divide Fibonacci 1? So if we write this Fibonacci 1, actually we can write this as 0 and 1. So this 1 has two preceding values before 1. No, it only has 1, which is 0. So we can tell Fibonacci 0 and 1 are our base cases. And then any other number greater than 1, we can actually simplify it. I mean, like we can divide it into smaller subproblems. So we can tell these cases as recursive case. So let's see how we can code this using Python. So like earlier, I'm going to define the function first. So my function will be Fibonacci, and I'm defining the parameters as n. And then first and foremost, we have to define the base case. So what are the base cases here? Fibonacci 0 and Fibonacci 1. So I have to tell if n is less than or equals to 0, return the result as what?
0.
0. If n is less than or equals to 0, I can ask the program to return the result as 0. Then I have another base condition, which is if n is equals to 1, I have to ask the program to return the output as 1. So if n is equals to 1, return 1. So here, as you can see, we have encountered two base cases here. So like I told you earlier, there can have one or more base cases in our problem. So the next step will be defining the recursive case. So I can tell else return what? Fibonacci of n minus 1. If you ask to print Fibonacci of n, then I can ask to print Fibonacci of n minus 1 plus Fibonacci of n minus 2. N minus 1 plus Fibonacci n minus 2.